Hello, students of algebra class. This is Ms. Prashauer. We are going to continue with our 8th unit of the year. We are continuing with that second half of Chapter 7, so this is Section 8 of Chapter 7. This will be actually the last section from Chapter 7 until we move into Chapter 8. Our goals for today are looking at what is a perfect square trinomial, what is the difference of two squares, and how can I, start to recognize these two special types of polynomials very quickly and efficiently. I can see them and then I can identify what's going on. Basically what we're talking about today are two, I won't call them exceptions because they follow the rules normal, but two special situations. Okay, we're not really learning any sort of new process of how to multiply or divide polynomials or anything like that. We're just looking at two special situations that generally occur when we're multiplying binomials. So most of our problems are going to take this kind of look today. We're going to continue with this idea of FOIL, but we're going to look at, like I said, two special situations. We're going to give them names, perfect square trinomials, the difference of two squares, and just start to be able to say, oh, yes, that problem is a difference of two squares. Oh, this problem is a perfect square trinomial. So the more we get comfortable with them, and the more quicker we can recognize them, the more efficient we are at doing our problems. Okay, so let's start. The one that we're going to start with is a perfect square trinomial, and what that is, if you want to write down this definition, that'd be good. It is a trinomial. Remember, trinomial means three terms. So we're talking about something like this that has 1, 2, 3 terms, and it's actually the result. It's the answer, I guess you could call it. That happens when you square a binomial. Okay, so here we have something like a plus b squared. We use this generic formula so that we can get an idea of how this might work no matter what a and b might be. So let's call our first term a, let's call our second term b in our binomial. This 2 here, we talked about this in class, it does not mean kind of distribute. Okay, this is not going to give us an answer of this. No. Because then we're forgetting the outer and the inner. Okay, we're doing the first with the a squared. We're doing the last with the b squared, but we're forgetting these terms here. So make sure that we understand that that's not what's going on here. So let's kind of look at what is happening in any sort of situation where I have a binomial a plus b and I'm squaring it. The first thing I want to do is write it out without this little 2 as an exponent. I actually want to write out a plus b times a plus b, because that's what that exponent means. Remember, x squared is the same as x times x. So a plus b squared is the same as a plus b times a plus b. All right, so let's kind of look at what's going to go on here. I'm just going to follow FOIL. My first is a squared. My outer is a times b plus ab. My inner is ba or ab. Let's write it in standard form in alphabetical order. And then my last is b times b, which is b squared. Okay. Whenever we do FOIL, we're generally getting 4 terms to begin with, but we're always seeing some sort of like term action that's happening here. And so this is our answer, no matter what. This 2 is going to be important later on as we get better practiced at this and we start seeing that what this coefficient is here is exactly the double of what we have here or here. Okay, a lot of times we have a 1 in front of a, but if we were to have something like x plus 3 squared, hopefully maybe we have an example. Oh, wow, that was like ESP right there. If we have an example here, we might as well go to the first of our group practice problems. We have x plus 3 times x plus 3. Okay, this is a binomial that we're squaring. What's going to happen, let's go through another example. The first is x times x, which is x squared. The outers plus 3x. The inners plus another 3x. And the lasts plus, oh geez, dropped my pen, is plus 9. 3 times 3. Again, we have these like terms here. So our final answer is x squared plus 6x plus 9. What you're hopefully seeing as we practice these lots and lots and lots and see the same thing happening over and over and over is that there's quite a relationship between this 3 here and the coefficient that we get on our middle term there. It's double. Okay, it's double. And that comes from, I'm going to clean this up here a little bit, the fact that we're always seeing this 2 here, no matter what A might be or B might be. Okay, so let's have you guys try this one. Okay, it's a little bit trickier, but you guys try that one. I'm going to write it out so you can see the work. When you come back to me, I'm going to write kind of silently here as you work. If I finish before you, just pause me. But go ahead and try B, and I'm going to try it up here as well. Okay, so what's happening? Let's see, 16y squared. I guess I'll do this one black. Plus 24yc. Okay, so I'm ready. If you're not ready, go ahead and press pause, but I'm ready. So this is the interesting part of this problem. Where is that 24 coming from? That 24 is going to be coming from, we have, when I multiply those two, I'm going to get 4 times 3, but then the double of that is 24. Why does that happen? Because I get a 12 here, whatever those multiply to me, when I look at my inners, and I get a 12 here when I get my outers. So I was going to kind of have double what's going on with the coefficients in your original problem. Okay, let's try some more in class tomorrow, because what we're going to do now, what I'm going to try and do is attempt to explain why this is. Okay, maybe you saw it here, you saw an example, okay, I see 6, Miss Pashauer, that's double 3. That's double 3 here. I see 24, that came from double what my coefficients were up here. But why? Okay, what is the mathematical proof behind it? And let's take a second to try and figure that out right now. And what I'm going to do is some geometry. I'm going to show you some figures to try and prove why that 2 is there. So let's go back to this idea of what is the area of a square. Okay, what is the area of a square? The area of a square is going to come from length times width. So if I have a square up here, that is A by A, the area is going to be A squared, right? That seems to make sense. So let's look at a square that has A and then B as its side lengths, and then the same thing here, A and then B. So really, the length of this side is A plus B, and the length of this side here is A plus B. The reason I'm doing that is because that sets up what our problems would look like if we were doing A plus B squared, because we're doing length times width to find the area of this square. So let me show you pictorially what's happening. So if this length, I'll do this one here in blue. If this length is A, and this length is A, this box here represents A squared. Okay? So that blue box, the area of the blue square, as I've written here, is A squared. What about this little bitty red square here? Okay, that is B up here times B. Okay, B times B is B squared. And what you notice is we still have these pinkish ones here. Okay? We have these pinkish ones here. And that's another reason to get you guys to understand why this is not A squared plus B squared. Okay, people would ask me in class, why can't I just do, why not, Ms. Bashauer? Well, here's the answer to that question. Look what happens when you start with a side that's A plus B times A plus B. Yes, you have this whole space in here that's A squared, and you have this whole space in here that's B squared, but what about this here? Okay, what about all that? Well, what happens is up here, we have B, and over here, we have A. So across, when I match up this one with this one, it's A times B. That's the area of that rectangle. Notice it's not a square, it's a rectangle, because A and B are not the same number. Here I have B, and here I have A. When I multiply A by B, length times width, I get AB. How many of these pinkish squares do you have, or purplish? Here I called them purple, I guess. How many of these purple squares do you have? Well, you have 2 of them. Their area is AB, but there's always 2 of them. Okay, so here I've given you a geometric proof for why this does not work. Why it's not simply A plus B in parentheses squared is not just A squared plus B squared. We can think about what the rules of FOIL say and say, you know, we're missing O and I, and there's a geometric proof for that there. Okay, so therefore we can always look at this as kind of a formula. And remember, this part here is what we call the perfect square trinomial. Okay, that is, oops. And I have a little table later on in our notes that we can write that down a little bit clearer, and it's very obvious. I have a nice summarization slide later. If you don't want to write this down now, you can write it down later, because I have both of our little special cases in our last slide of the day. But just so you're aware, that answer part here is called our perfect square trinomial. Makes sense because it's trinomial and it has 3 terms. Okay, this is what you start with to get it always, but the answer is called the perfect square trinomial. So that's our first special case. If you want to go back and review any of that proof, go back. It's not something you have to memorize. It's not something that you have to produce, but it is something that makes it make sense. Okay, it helps to solidify this. Okay, so our last and our second little special case is called the difference of 2 squares. Okay, the difference of 2 squares is obviously 2 terms, and it's difference, so we must be talking about subtraction somewhere. And 2 squares mean we're starting with one number, that's the square of something, and we're subtracting from it another thing that comes from the square of something else. So let's see what happens when we FOIL these, and if I can see and kind of, if I can explain this to you guys. If I were to FOIL this, I'm going to multiply it. The first are x squared, the outers minus 4x, the inners plus 4x, and the lasts minus 16. Okay, what's interesting about this special case is, look what happens to our 2 terms that are like terms. Okay, our 2 middle terms, our outers and our inners, our outies and our innies, are always going to cancel. Okay, they're canceling, or they're always going to cancel out. Okay, and what's left when these cancel is x squared minus 16. Okay, this piece comes down, this piece here comes down. And this part, that answer, when you do the FOILing, is called the difference of 2 squares. And it's just kind of a vocabulary term that we give to a interesting situation. Let me show you again how this works. We have x times x is x squared. Your outers minus 6x. Your inners plus 6x. And your lasts are minus 36. Again, these here are going to cancel out. Minus 6 and plus 6 is canceling. And I have x squared minus 36. Okay, remember that last objective where we talked about how you could start to identify when these things are going to happen when given a problem? Is there any way you could summarize what this problem looks like and what this problem looks like that might tip you off that you might have an answer that is the difference of 2 squares? Okay, these look almost identical, right? Okay, they're almost identical, not really identical. But what's different? Okay, the difference that you should be seeing is that plus or that minus in the inside. Here it's plus 6, here it's minus 6. The reason that situation leads to these terms canceling out is our outers and our inners will be opposites. Okay, we talk about opposites as 5 and negative 5. Okay, those are opposites, things that will cancel. So negative 6 and positive 6 are opposites. I'd like you guys to try these here and see what happens. And I will reveal the answers to you when you come back. So try B and C. Pause me right now, and I'll have the answers when you come back. All right, ladies and gentlemen, I assume that you're back. B is going to give you x to the fourth minus 4y to the second. Okay, these are the difference of two squares because x to the fourth comes from x squared times x squared. Okay, this one comes from 2y times 2y, right? That's why it's called the difference of two squares. These numbers come from something that gets squared. Here we have x times x gives us x squared, and this one we have 6 times 6 gives us 36. That subtraction sign is just part of the formula because it's the difference of two squares. Okay, and the third one is 49 minus n squared. This is the difference of two squares because 49 comes from 7 times 7, and n squared comes from n times n. Okay, so that is our second little special case when we start talking about polynomials. And like I promised you, I have a nice, clear little box here that you guys can write nice and big, outline it, make it stand out as far as the summarization of our notes today. Okay, we have the perfect square trinomials right here, and we have the difference of two squares. Okay, the part that is the perfect square trinomial is this part here, what the result is. The part that is the difference of two squares is this here, the result after you FOIL. Okay, so hit pause, copy that down. Come back to me when you're done. All right, hopefully you have that copied down. And make sure that you understand our objectives of the day. Remember how we, if I asked you to produce a perfect square trinomial, would you know what to produce? If I asked you to produce something that would be the difference of two squares, could you write an example? And then let's really start to be able to recognize these quickly and efficiently when we see them on our homework and our tests and our quizzes. All right, ladies and gentlemen, we're all done for the day. Have a great evening.